Hello, and thank you for joining me today. Give me just 1 second while I get this PowerPoint presentation pulled up on screen. And there we are. So my name is Mason Paddie of the University of Texas at Tyler Mechanical Engineering Program, and my semester project is an analytical comparison of a simulated PEM fuel cell and internal combustion engine. So a little bit of an overview. We're going to start with what is a fuel cell and then work into the background on my application. And for my application, we'll start with the assumptions, and then we'll work into the energy analysis and some of the simulations that go with that. And then we'll work into the degradation simulations, cost analysis, and then some of the lifetime calculations for that. And then we'll talk about some of the issues to overcome before concluding the presentation. So to start, what is a fuel cell? A fuel cell is an electrochemical device that converts chemical energy into electrical energy. The overall chemical reaction inside of a PEM fuel cell is represented by the chemical equation seen below. So 2 hydrogen and an oxygen produce 2 moles of water and heat. And the figure on the right in figure 1 kind of just shows a model of this chemical equation in action. So hydrogen enters at the anode side, and at the anode, an electron is stripped away from the hydrogen, and that electron is pushed through a wire, thus producing the electric current. The hydrogen cation then transfers to the electrolyte and combines with oxygen at the cathode in order to produce water, which then leaves the fuel cell. So for some of the applications, background and purpose. So the application is a comparison between fuel cells and combustion engines in automotive transportation. A multitude of fuel cell types mean fuel cells can be used for a wide range of purposes. And parameters such as lifetime duration, lifetime cost, efficiency, and power density we calculated and compared to literary references. So as just stated, there's a multitude of fuel cell types that can be used for a wide range of purposes. For automotive transportation, it is widely accepted that a proton exchange membrane fuel cell is the best due to its small size, lightweight, and quick startup time. And the fuel cell will power a compact passenger vehicle. The fuel cell receives hydrogen fuel at standard conditions and pure oxygen at the cathode. In production, a fuel cell stack is part of a production line of 500,000 units. The PEM fuel cell operates without combined heat and power due to low operating temperature. Water exits the fuel cell as a saturated liquid. The thickness of the electrolyte is 15 microns, and this is the thickness that is recommended for automotive applications. The transfer coefficient is 0.5. The fuel cell operates at 70 degrees Celsius, and the fuel cell is in operation for 400 hours per year. And the 400 hours per year was chosen because I wasn't really getting a consistent answer for my references. One reference would say about an hour per day of driving for the average person, while another reference was saying that a driver could spend up to 432 hours, the average driver up to 432 hours per year of driving. So I picked 400 hours just because it was a nice round number for calculations, and it's a general average of about how much a person would drive in 1 year. So for the overall simulation starts with the green box there. That green box is our optimal parameters, as I'll refer to them. This is what the fuel cell would be right off of the production line when it's running at its absolute best capacity. That is all within the green box. And then within the orange box is the degradation simulations, and that will actually take time into account and will compute the degradation over that time frame. So for the energy analysis, the efficiency and reference exchange current density will be evaluated as they're just 2 parameters of importance. The amount of hydrogen and oxygen needed is found from chemical properties, and the water production is found in a similar way. The heat production is then found from the amount of losses. So for the simulation, this is that green box that was within figure 2. Within this simulation, no time is taken into account. So this is just the fuel cell as it would operate at optimal parameters right off of the production line. And you can see some of the major parameters in the simulation below, but we will get to some of those as well in the future slides. Okay, so for how the efficiency calculation was done, the efficiency calculation was done by taking the quotient of the output work and the output power and the power potential of hydrogen. The output electrical power is the product of the current and the output voltage. And then the power potential of hydrogen is found using Faraday's law. And those 2 equations there are for the molar flow rate of hydrogen. And then the power potential of hydrogen is the product of the molar flow rate of hydrogen and the higher heating value of hydrogen. And the higher heating value is taken because water exits the fuel cell as a saturated liquid. And this equation will then reduce down to just a function of the output voltage. And that efficiency was determined to be at optimal parameters, approximately 51.77%. So for the reference exchange current density, this is a parameter of importance when solving for our losses, our voltage losses in our fuel cell. So in order to solve for the reference exchange current density, a TAFL plot is built from the TAFL equation for overpotential. And then you take the linear section of this graph and extrapolate that down to the x-axis. And where that line intersects the x-axis is our reference exchange current density. And that is found to be about 0.99 amps per centimeter squared when running at optimal conditions. So for our energy analysis, these parameters can be seen in figures 2 and 3, but they're also placed into tables 1 and 2 just for quick reference. Table 1 shows some of the optimal parameters from our fuel cell, such as the voltage, voltage loss, power density, and a few other parameters of importance. And then table 2 shows the flow rates required for the hydrogen and oxygen, and then the flow rate of water that would be produced in the fuel cell. One thing to note about the flow rates is that they are on a per centimeter squared basis. That is because there is no membrane area taken into account anywhere within the simulation. Therefore, the flow rate will be in terms of the membrane area. Okay, so now for the degradation simulation, this is that orange box that was within figure 2, and this will actually take time into account and the degradation over that time. This is not much different than the optimal simulation. The only difference being the incorporation of the degradation rate, and that degradation rate is integrated over time and subtracted from the output voltage in order to determine the voltage at that specific point in time. One thing to note is that the degradation rate is being multiplied by a random number generator. This is so that the degradation is not constant over time, and it's just there to kind of simulate what a real system would be like, because a real system would not have a perfectly linear degradation. It would be a little jagged, and that random number generator will cause that sort of jaggedness that we're looking for. And it is set with a mean of 1 and a variance of 1. This is so that our average degradation rate over time is still that same degradation rate that was specified by the MATLAB function. And one other thing I want to draw your attention to is at the very top of the simulation, you can see how there is a 0.95 gain on the output voltage. And this is just telling us that our failure voltage will be 95% of the optimal voltage. Okay, so for the cost analysis, first, the lifetime duration is found from the Simulink model, and the degradation constants are used from reference 22. The total upfront cost is determined using information from reference 5, and then platinum usage was estimated over the lifetime. And an equivalent uniform annual cost analysis will be done, assuming an interest rate of 5% and discount rate of 15%. Okay, so for the lifetime duration of a real fuel cell, the lifetime duration is found by first running the fuel cell for about 200 hours or some fraction of the estimated lifetime. And then after this 200 hours, you extrapolate the degradation data over time to determine at what time the voltage will reach the failure threshold. As was stated in the previous slide, the failure threshold for this project was taken to be 95% of the maximum output voltage. And for the purpose of this project as well, there was no 200-hour time frame that was ran prior to the fuel cell actually being completed. The fuel cell is just ran over the entire length of time, and then it is found where the failure threshold is met. And the equation seen on screen is the equation that was used to actually generate the degradation graph. So lifetime duration as calculated by the Simulink model that was designed can be seen in the graph, the figure 7. And 5 trials were conducted to determine an average lifetime at a 99% confidence interval. This is because the random number generator made it so that it was not the exact same lifetime duration every time. When plugging in these values at a 99% confidence interval, we get an average lifetime of 6.42 plus or minus 0.11 years. And that is found from that 400 hours per year estimation that was assumed. Okay, so for the lifetime cost, table 3 shows some of the upfront cost in terms of area for a PEMFC. And then assuming that the membrane must be replaced annually and platinum must be replaced monthly, an annual cost of about $610,000 per square meter is considered. If the area of the membrane in square centimeters and the lifetime in years is known, the lifetime cost can then be found with the below equation. Now, no area of the membrane has been taken into account anywhere thus far, but to calculate the area of the membrane, it is assumed that a fuel cell stack must provide at least 60 horsepower. When applying this to the power density calculated by the Simulink model, the required amount of membrane area is about 54,700 square centimeters. From that, we can then determine the total lifetime costs. And from the total lifetime costs, we can determine the equivalent uniform annual costs. And when determining the equivalent uniform annual cost, this number comes out to be $732,724.79 per year, or about $232 per kilowatt hour. So for the literary comparison, the EUAC of an internal combustion engine vehicle is about $1,200 per year, but includes the entire vehicle, not just the engine. And the energy cost is about 4 cents per kilowatt hour. And although the internal combustion engine vehicle considers the cost of the vehicle, not just the engine, a fuel cell vehicle, the most of the cost of a fuel cell vehicle would go towards the engine itself. So the EUAC would not be changing much on a percentage scale. It would not be changing much. Over the lifetime of the internal combustion engine, it will produce about 136,000 pounds of greenhouse gases compared to the zero emissions of the fuel cell. So this is one area where the fuel cell has a significant advantage. And then a gasoline combustion engine operates at an average of 20% thermal efficiency, but diesel combustion engines can increase the efficiency to 50% compared to the about 51% that was calculated for the fuel cell that was simulated. So the fuel cell does have somewhat of an advantage in the efficiency category as well. But some issues to overcome. The cathode and anode both use platinum as a catalyst, and this is where most of the cost of the fuel cell actually goes towards. In order for fuel cells to be commercialized, the platinum as a catalyst needs to be addressed, whether it be we use less platinum for the catalyst or whether we use a different material, whether platinum price goes down. Something needs to happen in that aspect for fuel cells to be commercialized. And then the hydrogen fuel is highly sensitive to impurities. This won't directly affect the performance of the fuel cell, but the impurities within the hydrogen fuel will erode the membrane over time, and holes in the membrane can significantly decrease the functionality of the fuel cell and also decrease the amount of time in between replacing your membranes. And then future recycling companies may have issues distinguishing the type of fuel cell and cause damage to the parts. So the difference in disassembling one type of fuel cell is different than assembling another type of fuel cell. And somebody who's not very knowledgeable in fuel cells may not know the different types of fuel cells and may disassemble this fuel cell incorrectly and cause permanent damage to those parts. And the high flammability of hydrogen could also be a concern at refueling stations. The high flammability of hydrogen is part of what makes it such a good fuel source. It's a lot more flammable than gasoline, but this also makes it slightly more dangerous. And things such as smoking would need to be taken into much more seriousness than they are currently at refueling stations if hydrogen was the fuel instead of gasoline. So in conclusion, a proton exchange membrane fuel cell is simulated in the Simulink, and parameters were compared to literary references of an internal combustion engine. The fuel cell has a lifetime of approximately 2,600 hours with a maximum efficiency of 51.77%. And issues in costs and longevity must be addressed if the PEMFCs are to be successfully commercialized. Okay, and there are some of our references. And thank you for your time. I hope you'll have a wonderful day.